this arc length for polar curves, and we've already got the formula here, but where does it come from? Well, if you remember, our arc length for parametric was this. So if we could create dx d theta and dy d theta and do a little simplifying, we get this. So if you remember, x is equal to r cosine theta. So dx d theta would be r prime cosine theta plus minus r sine theta. And then y is equal to r sine theta. So dy dx would be r prime sine theta plus r cosine theta. Now, if you take these and you square them and add them together, and I'm going to leave that up to you because I don't want to waste your time in a video, you will end up with r squared plus r prime squared. So we end up with this situation going on for our integral. Same theta because we're dealing with theta here. They're both functions of theta from a to b. So we end up with this for our formula. So if we want to find the exact length of a polar curve, we're going to go from 0 to 2 pi. And then what we need to do is take the square root of r squared plus, and then we now need the derivative. So r prime, let's write r first. R is equal to 5 theta. So r prime would be 5 theta natural log of 5, if you remember that from our derivatives. So if we plug that in here, we would now have the arc length, which is giving us this. So as we move from 0 to 2 pi, that's our arc length. So it moves around like that. See how it's scrolling around all the way to there. So that whole arc length is that value. So if we take it now and we plug this in our calculator, we go math 9, 0 to 2 pi. And I know it says exact, but we're going to do an approximate for this one and an exact for that one. 2 pi. That's not pi, that's theta. 2 pi, second square root, and then inside we put parenthesis, and then 5 to the power of theta. And I'm in polar form right now to have those thetas, but you can use any variable you want. Squared plus, and then we write the other one, 5 power theta, natural log of 5, and then we square that one. So it's just r squared r prime squared, or r prime squared r squared d theta, and you hit enter. You can see there's our 29,015. Let's put at least one decimal on there, 0.6 would give us our arc length, which matches what we had here. So the length of that arc is 29,015.5629,678. So you could evaluate the integral if you want to find the exact value, but like I said, we're doing the approximate here because I don't have enough room. We'll do exact on the next one. So all you're doing is finding r prime and r, which we already are given, and you're plugging them in and evaluating the integral. So this one, we need to find r prime. So that would become -2 sine theta. And we know our r is 2 cosine theta. So now when we place it in our integral, we go from 0 to pi, -2 sine theta squared plus 2 cosine theta squared. Doesn't matter who comes first. D theta, and that will give us our arc length. So we have 4 sine squared theta plus 4 cosine squared theta, the radical. That 4 can be factored out and give us 2. And sine squared plus cosine squared theta is 1. So we end up with 2. 0 to pi d theta. So this would be 2 theta. Pi to 0. So it's 2 pi. So that arc length would be 2 pi. Let's take a look with Desmos. All right, so as I take my 2 cosine theta and I go from 0 to pi, You can see it makes one circle. So that makes complete sense. Our circle is a radius of 1. So that means we'd have 2 pi r all the way around. So 2 pi times 1, which would give us that perfect arc length that we're talking about here, which is 2 pi. So that's it for arc length. You just have to take the derivative, plug it in as a square and a square of the r itself, square root it, and you get the arc length.